Hello everyone. Today we're going to talk about revegetation as a management technique for riparian buffer zones. But before we jump into what this management strategy does, it's important to understand what buffer zones are. Broadly speaking, buffer zones are strips of vegetation, including trees, shrubs, and grasses, that are planted next to waterways. These zones can be naturally occurring, but due to anthropogenic influences, many have been destroyed or compromised. When buffer zones are healthy, they're typically divided into two sections. The first section is the streamside zone, and it's located immediately adjacent to the water corridor. This area should be populated with water-tolerant trees and large shrubs. The second section is the middle zone, and it should be planted with fast-growing native species and smaller shrubs that are shade-tolerant. Occasionally, like in the diagram we have here, you'll also see a third zone called the outer zone, but this is typically reserved for direct human use either as agricultural land or housing development. Now, as I mentioned before, many of the naturally occurring buffer zones have been removed or replaced by different land use types, resulting in a need for managed buffer zones and widespread planting efforts, aka revegetation. Put simply, revegetation is the process of replanting and rebuilding areas of land that have had their natural vegetation cleared. This is an example of a restoration management approach, as most planting efforts look to recreate the naturally occurring buffer systems. But it's not as simple as dropping a few seeds into the ground. For revegetation to be successful, a significant amount of pre-planting has to occur. First, the soil must be prepared for the new vegetation. This includes mechanical preparation like clearing non-native plants, removal of stones or debris, leveling or grading of the ground, and sometimes even the addition of new soil. Analysis of the existing soil is also recommended because runoff and other pollutants can make said soil inhospitable to buffer zone plants. If that's the case, managers need to develop a plan for correcting anything from pH balance to nutrient levels. Next, appropriate plant species must be chosen. While the general type of plants will remain the same in each buffer zone, native species vary considerably from system to system. Revegetating with native plants is preferred because they're the most likely to thrive in the existing soil and climate and to provide the greatest benefit to the riparian system. Once all of this preparation is done, we're ready to plant. For revegetation, two primary methods are used for planting: direct seeding and transplantation. Direct seeding is when seeds are sown directly into the ground. The downside to this method is that it can take years for trees and larger plants to establish, but this approach is more effective from a cost and labor standpoint. It also typically leads to trees with superior root systems. On the other hand, transplanting is when plants are grown in nurseries and then transferred to the area in need of replanting. This method is more expensive, but the results of the revegetation effort are apparent much more quickly. Regardless of which sowing method is used, once the plants are in the ground, they're typically mulched to avoid a loss of soil moisture, lessen soil erosion, and protect soil temperature. In some locations, the new vegetation will also get watered, but oftentimes the stream or river system itself provides for the plant's water needs. From there, managers must monitor the area and assess for the successfulness of the program. So why do we go through all this effort to revegetate buffer zones? The first reason, and arguably the most important outcome of revegetation, is the improvement in water and soil quality. As the reestablished plant roots grow, they intercept surface water and filter out sediment and pollutants. This is especially important for buffer zones adjacent to agricultural land, where runoff from crops can wreak havoc on a stream's health. Long-term improvements in water quality provide provisioning services by increasing downstream fish stocks and reducing the amount of processing water needs to be usable. These plants also help stabilize the banks of riparian systems, lessening erosion and preventing sediment from entering the water system too quickly. This leads to mitigation of flood effects as well, with steadier buffer zones able to absorb more water. Beyond being good for the river itself, this regulating service helps avoid riparian encroachment on farmlands and other human infrastructure. And lastly, revegetation provides habitat for wildlife and pollinators. The return of wildlife to these areas aids in pest control, provides hunting opportunities, and improves the health of plants relying on pollinator services. These recreational provisioning and supporting services are what make the cost of revegetation worthwhile. However, as I briefly touched on before, revegetation does have some limitations. The biggest issue is that plants take a long time to establish themselves, meaning that their beneficial effects can sometimes take years to come to fruition. This can frustrate land managers and make the public skeptical of revegetation's value. Revegetation is also most effective when used preemptively. If a riparian system has already seen massive erosion or sedimentation, the addition of native plants will only improve the area so much. As humans are notoriously reactive, this can limit the situations in which revegetation can be applied. And lastly, certain geomorphological attributes can render revegetation totally ineffective. These conditions include areas of geologic instability, near vertical bluffs, and overly inundated areas that are too wet for the vegetation to take hold. If a land is too hostile for young plants, revegetation becomes an infeasible management tactic. But despite these potential limits, revegetation is still widely used. And one such example was the work done at Wilson Creek. Wilson Creek is a 55-kilometer long fourth order tributary of the Salt River located in Kentucky, and is located in Bullitt and Nelson counties. In 2003, the creek was heavily channelized, resulting in rapid bank erosion and decreased water and soil quality. To address these concerns, multiple management strategies were used, but one of the primary focuses was the revegetation of riparian buffers along a 2,670-foot reach of the creek. The revegetation corridor was divided into two sections, an inner and an outer zone, and the inner zone extended 16 feet from either side of the stream and was stocked with shrubs and trees adapted to occasional flooding and frequent disturbances. Trees were planted with a 6-foot by 6-foot spacing and were interspersed with native shrubs and grasses. The outer zone extended 32 feet beyond the inner zone and was planted with trees and shrubs accustomed to occasional flooding and saturated soil. This vegetation was planted 16 inches on center and included 15 different species. In both zones, transplantation was the primary method for sowing. To facilitate their growth, as you can see from this picture here, pulled from their work, the plants were also covered in burlap to prevent soil erosion, and additional plantings were added in 2004 and 2005, partly just to increase the overall number of woody species and partly to make up for some lost seedlings due to unusually wet conditions the year prior, which you can also see in this picture. So now comes the big question. How effective was revegetation at improving water and soil quality and preventing soil erosion? Fortunately, the answer seems to be fairly successful. A group of third-party researchers performed long-term monitoring of the site and gathered data on extractable soil nutrients and water oxygenation levels, among other ecosystem health indicators. They took their first round of measurements in 2004 when the initial revegetation restoration was completed, and again in 2015. As you can see from this figure here, extractable nitrate and ammonium increased across all reference sites. This indicates that the soil was able to support continued plant growth and that runoff into the riparian system had declined. Similarly, the soil carbon-nitrogen ratio, as shown on this diagram, decreased over time, indicating a return to the preferred range. This is a key marker of soil health and shows long-term development of a healthy system. Relatedly, their monitoring also found improvements in key water quality parameters and an increase in dissolved oxygen, which is very good news for the aquatic plants and animals. All of these changes led to improved habitat for terrestrial wildlife and fish, and aesthetic improvements for those living in the area, like you can see here. Unfortunately, no data was available regarding erosion rates, but the researchers did mention that the bank had stabilized, indicating that at least some reinforcing effects from the revegetation occurred. Still, given the improvements in soil and water quality, both the monitoring researchers and myself feel that this restoration effort was a success, due in no small part to the revegetation of the buffer zone. And that's all I've got. Here are my citations. Please feel free to let me know if you have any questions.